ST Lab in France. In this presentation, we are going to present a distributed energy-efficient clustering approach based on Kruskal Heuristic for IoT networks. In this presentation, we will try to cover the main part of the work according to the following plan. First, we start with an introduction that explains the field and highlight the problem. Then we discuss some drawback faced by the existing approach before introducing our contribution. After that, we discuss the simulation result and finally we conclude our work. First, let's start with a quick introduction. The IoT networks represent an emerging technology. They are used in several research domains, from military to environment monitoring and even healthcare. IoT network consists of a large number of intelligent small devices deployed over a large area. They collect information and relay them to a central controller or a base station. Such large-scale and dynamic network, the clustering represents an efficient technique proposed to improve the energy consumption. It emerged as a solution for routing problem, topology management, scalability tolerance, as it reduces the size of routing table, and it also conserves the communication bandwidth, which represents a critical resource. Motivation. Energy optimization technique in wireless network mainly employ clustering model to ensure the network durability. However, in most cases, clustering approach are generated using the single hop clustering model, which may obstruct the scalability in case of a large network. Also, clustering approaches mainly focus on the short-term vision of energy efficiency and mostly consider devices with non-rechargeable battery. In this work, we introduce a long-term energy-efficient clustering technique based on a long-term vision of energy optimization. Our approach uses an unequal multi-hop clustering model to extend the network durability by considering the degradation of battery during the clustering process. The idea is to structure the network based on the state of health of devices' batteries to increase the network durability in the long term. In this part, we will discuss some drawback faced by the existing clustering approach. First, the most part of existing clustering methods assume a centralized clustering. The problem with such methods is the reduced scalability and the central point of failure, which is faced in case where the base station fails. Also, the existing approach assumes an equal energy consumption without considering the network node distribution. And also, the existing approach are suitable for non-rechargeable battery. They mainly consider the actual residual energy to evaluate the performance of their approaches without considering the battery degradation. Two typical communication models are assumed during the data transmission. The first one is the single hop transmission, where every node sends the collected data directly to the base station. The problem with such model is the limited transmission range, and also the node furthest from the base station will exhaust most of their energy to relay their data. This model suffers from a poor bandwidth management and can cause an eventual collision and interference problems. Second model is the multi-hop transmission. This model is typically used to aggregate the node data over several hops to reach the base station. This model is more efficient, however it suffers from an energy hotspot problem. Indeed, nodes or cluster head near the base station will exhaust most of their energy earlier due to the aggregation of other data coming from the routing tree, which will lead to a disconnection event. With our approach, in order to load balance the energy consumption among cluster heads in the network, we assumed an unequal clustering technique, where the cluster size is relative to the distance between the cluster head and the base station, as shown in the following figure. With such structure, clusters near the base station will spend less energy on regrouping cluster data and focus on relaying the data coming from the routing tree. On the other side, clusters further from the base station regroup more members and consume more energy on regrouping the cluster data and spend less energy on aggregating these data to the base station. Moreover, the Kruskal Heuristic computes a minimum spanning tree within each cluster. With this approach, network members constitute initially a separated singleton tree, and after each step, these clusters come together in PA. The connection between the isolated cluster is made using the shortest path that relays this tree without forming a cycle. This process is repeated until merging all the trees into one cluster. The heuristic results in a single minimum spanning tree, also called MST, obtained using successive connection between isolated trees. Kruskal heuristic require an additional time to form the clusters. However, the generated structure optimize the energy consumption and allow the tolerance of a dynamic network topology. We notice that the approach which focuses on improving the energy consumption in wireless network mainly addresses the amount of energy consumed. They use the battery state of charge or the residual energy as a metric to evaluate the durability performance without assuming the battery aging aspects. These approaches represent a short-term vision of energy efficiency. Indeed, node battery follow an aging process that include other factors than energy consumption, such as the battery temperature or the charging and discharging speed. These aspects degrade the battery capacity and need to be considered in order to address the network durability in the long term. In this context, we elaborate the problem of considering the battery aging to optimize the network lifetime in the long term. The objective is to increase the battery durability over several recharging cycles by considering the battery aging aspects, or the state of health of the battery, during the clustering process. This figure represents a comparison between the short-term lifetime, represented by one recharging cycle, typically considered by clustering approaches, and the long-term lifetime, represented by all the recharging cycle until the battery is completely depleted. To clarify our idea, let's consider the network routing example illustrated in this figure. In this routing scheme, 3 nodes, node 1, 2, and 3, can relay the data of the source node S to the base station. With a classical approach, either node 1 is selected to aggregate the data because it has the highest residual energy, 80%, or the node 2 because it consumes the lowest amount of energy. However, when considering a long-term energy efficient vision, the optimization of the battery state of health leads to select the node 3. Although this node has the lowest residual energy, 40%, it represents a better state of health, 51%, and the sustained damage is minimal, 0.8% per transmission. Therefore, instead of only considering the residual energy or the battery state of charge during the clustering, our approach adopts a long-term vision of energy optimization by considering the battery state of health to reduce the material substitution and increase the network lifetime in the long term. The proposal reduces the number of generated clusters by using a weight-based technique in the cluster head election process. The weight constraint combines 3 metrics: the battery degradation, the battery state of health, and the neighborhood connectivity. With such approach, nodes that will endure a considerable battery degradation will not be granted as a cluster head to preserve their durability, which increase the network lifetime in the long term. The following figure illustrates a comparison of the state of health of devices' battery after several rounds with 400 deployed devices. The red node represents the dead devices. With the equal multi-hop clustering scheme, the figure in the top left, the imbalanced distribution of energy consumption led to an energy hotspot problem. The other approaches, which use unequal clustering, show better energy distribution. However, they do not take into consideration the battery aging. Therefore, we observe that some nodes exhaust most of their energy to transmit their data. Our contribution represents the less colored figure. It shows less variation of energy level among nodes, which reflects a better distribution of energy consumption. This figure represents the average cluster's cardinality according to different value of network density using our approach against similar protocols. The proposed scheme generates a reduced number of dense clusters according to the node density and to the battery state, which in turn improve the clustering efficiency and lead to a better energy preservation. Therefore, the proposed approach shows better performance compared to similar approaches. It improves the cluster cardinality by an average of 38%. The following figure illustrates the average energy consumed by network devices during the clustering phase in the short term. We observe that the energy required for the clustering increases along with the network density due to the amount of messages that need to be exchanged to generate the topology. Our proposed approach consumes more energy compared to the other approaches. This point may be assessed as a shortcoming. However, the results are acceptable because the consideration of the state of health in the weight metric display better performance in the long term. The following figure illustrates a comparison of our clustering proposal compared to the conventional approaches by considering the long-term network lifetime with variable node density. In this case, the proposed approach shows better results. This enhancement comes as a result of exploiting the battery state of health metric. Indeed, rather of using the conventional battery state of charge or residual energy during the clustering, our approach considers the battery degradation before the election of the potential cluster heat. Moreover, the proposed approach assumes an unequal clustering scheme which alleviates the hotspot energy problem and further balances the energy consumption. Therefore, the approach exhibits better lifetime performance compared to the classical approach. And finally, as a conclusion, in this work, we presented an efficient clustering technique based on a long-term vision of energy optimization. We take into consideration the battery degradation aspect in the clustering scheme, which enhances the battery behavior and extends the network lifetime in the long term. This consideration will give a positive impact on the future green computing environment.